Hello and welcome back to the World Pipelines podcast. With me for this episode is Rustem Khalikhan, Junior Project Engineer at DNV, the global independent risk management and assurance provider. DNV primarily acts as a classification society for the maritime industry and as a technical advisor to the energy sector. Headquartered in Norway, DNV sets industry standards for safety, sustainability, and quality, and operates in over 100 countries. Rustem is based in Milan, Italy, and he is a civil and environmental engineer. He previously worked in academia and joined DNV 3 years ago as a structural engineer in the verification team of the offshore, midstream, and downstream departments. Since then, he has worked on the structural verification of offshore assets, as well as taking part in projects related to pipeline damage and fitness for purpose assessment, and research on pipeline integrity management and pipeline repurposing. Now, the starting point for our conversation today is RDNV-RP-F113, a standard that has been in existence for nearly 20 years, and one that has had quite an impact on subsea pipeline repair. World Pipelines helps oil and gas pipeline professionals stay informed about the midstream oil and gas sector, offering technical articles, regional briefings, project and contract news, and think pieces on pipelines all over the world. Register to receive a print or digital copy at worldpipelines.com and search World Pipelines on LinkedIn to join our community. So thank you for joining the podcast, Rustem.
Thank you. I'm very cheerful. Well, for us, it's morning, and I'm glad to be here.
Now, before we get into the detail of this standard, maybe you can set the scene for us. So what was the industry challenge that this particular recommended practice was originally trying to solve or trying to address?
Okay, so one of the key challenges faced by the offshore industry was that although pipelines were designed to very high reliability standards, sometimes people may say too conservative, but still there was no consistent industry framework for what should happen when a subsea pipeline was actually damaged. Repair systems existed, but operators often approached preparedness and qualification and repair planning differently from one another. And historically, subsea repair was still viewed as a contingency activity, something that would hopefully never happen. The problem was that when damage did actually occur, decisions had to be made quickly and often under significant operational and obviously commercial pressure. The industry needed guidance not only on repair hardware, but also on repair qualification, damage assessment, and obviously the preparedness. The RP-F113 was developed to establish a common approach for designing, qualifying, and implementing subsea repair systems. It transformed the repair from a reactive emergency response into a structured engineering discipline at the end of the day. It recognized that successful repair starts long before damage occurs through preparation, risk assessment, and the qualification of the repair systems. Here, it's also important not to forget that the repair system, the hardware or software, was commonly requested by insurance companies to withstand a strategic project like a transcontinental gas link. But it was not the case for subsea pipeline networks, particularly in very deep waters, for which the request is actually relatively recent.
And in terms of what RP-F113 covers, whereabouts does it sit in the life cycle of a pipeline?
First, it covers the qualification and application of subsea repair technologies and repair strategies for submarine pipelines. Technically, it deals with the pipeline repair systems and fittings that include clamps, mechanical couplings, T-branch connections, hot tappings, and many more. Importantly, it also covers the procedural requirements or recommendations. So these are repair preparedness, selection of repair methods, manufacturing and testing requirements, as well as lifecycle management. The standard occupies the last quarter within the DNV's broader integrity management, so the repair and intervention portion of the pipeline integrity management cycle. And in this particular framework, it is not treated as an isolated activity, but as a part of a continuous process of risk assessment, inspection and monitoring, as well as integrity assessment, and obviously mitigation and repair. A key message at the end of the day of the RP-113 is that the technological approach to repair should be considered from the very beginning and throughout the pipeline lifecycle, not only when or after failure occurs. And quite honestly, I would like to point out, even from several client inquiries this year, that this message has been heard.
Great. The average observer might think that standards are invisible. They might only notice that standards exist when something goes wrong. Do you think that the industry fully appreciates the role that standards play?
I have to admit that I don't really know if I can talk about the sentiment in the industry. In my humble opinion, people do tend to notice standards only either when something goes wrong or when the project constraints arise. So for example, if there is a direct requirement from the end user to follow a specific code, and then designers do get into standard detail. At the same time, I also see the standards, guidelines, and recommended practices as a common engineering language. Standards help ensure that operators, contractors, manufacturers, certifying bodies, regulators are all working from the same technical basis, or at least trying to do so. And so not to wander off, I cannot fully say if the industry does or does not appreciate the standards. What I can say is that there is a confidence when the industry uses them. And then there is a general trend towards harmonization of these standards so that the standards are actually well put together. And without the codes and the RPs, every project at the end of the day would have to reinvent the wheel every time. Consequently, the methodology and acceptance criteria would differ. Whereas in offshore projects involving many stakeholders in different countries, consistency is crucial. The real value of the RP-F113, in my opinion, is not simply that it belongs to a complete, if I may, DNV standard ecosystem and defines how repair should be performed. It creates confidence that repair systems will perform when they are needed, often many years after being designed and qualified. And as my senior colleagues like to say, at the end of the day, you cannot have a draft of repair technology. You actually need it to work.
And these offshore projects we're talking about, what are the real world scenarios that we're dealing here? What typically goes wrong?
Well, first, fortunately, nothing goes catastrophically wrong. However, pipelines operate for decades and in challenging environments, and damage mechanisms do occur. Examples include dropped objects during offshore construction, dragged anchors, fishing gear, interaction, excessive free spanning, geohazards, that's a big one, such as landslides, seabed instability, turbidity currents, corrosion damage, roughly 1/3 of the cases, fatigue cracking, and cold cracking, like due to hydrogen, for example. Here, it is always about a specific case with its own context. Like external mechanical damage is more common in busy areas where you have deficient vessels, for example, whereas repurposed hydrogen pipelines typically experience completely different sets of problems. One lesson that comes from all the fitness for purpose assessments that I was involved in, at least, is that not every damage indication actually automatically requires a repair. The key challenge is actually the determining of what the defect is, its exact location, its dimensions, the root cause. So in case of an external interference, again, you also need the dimensions of the thing that did the damage. So the anchor, the rock, whatever it is, whether and how it compromises the structural integrity, whether operation can continue safely, because at the end of the day, this is the main topic there, because you may have major damage where you can automatically you need to repair, minor damage when you do need it, but a lot of the cases fall in the middle ground where you don't really know. And lastly, whether monitoring is sufficient or whether immediate intervention is actually necessary.
So it's an investigative process in that respect.
For sure.
Okay. One thing then I would like to focus on is DNV's emphasis on method and philosophy. From what you're saying, there is a method to this. It's not just a set of rules. How would you describe DNV's approach to design and repair?
To me, this philosophy, not even only in design and repair, but in general, the DNV philosophy lies in being fundamentally risk-based and performance-based. So you really have to dig into the probability side of that. And the goal is not simply to prescribe rules, but to understand how a structure behaves under realistic loading conditions and then demonstrate sufficient reliability. At the end of the day, you can always go conservative. as long as it's proven to be conservative. But typically, you would like a realistic assessment to save the costs without compromising on safety. And DNV's ecosystem of standards and guidelines and the general approach allows just that. The ecosystem may be seen, in the case of pipeline, for example, it may be seen throughout the pipeline framework. So it's the standard F101 for design, F113 for repair, F116 for integrity management, plus numerous joint industry projects for more specific cases. The approach here relies heavily on quantifying uncertainties and engineering verification. And the standards actually aim to provide robustness rather than simple compliance. And that's particularly important for repairs because, as mentioned, every damage scenario is unique. And the standards therefore provides an engineering framework rather than a simple checklist.
Now, you mentioned this earlier, I think. Do you ever hear criticism that standards like this are too conservative, that they slow things down? And if so, what's your response to that?
As a verification engineer, I do hear that conservatism claim quite often, and sometimes even as a direct response to comments that I raise. My response would be related to this common language aspect that I mentioned before. So the standards may be seen as common language, whereas industry shareholders may use. And given the difference between the shareholders in the energy sector, there must be something that all the shareholders understand. So it's like the key to a code or the language. And I see probabilistic approach to failure and quantitative risk assessment that typically is the conservative part there as the keys that everybody has to understand as well. Thus, my response is quite simple. Standards are there not to complicate one's life at the end of the day, but to ensure safety based on probabilistic and quantitative methods. Conservativeness is often claimed when dealing with, like in the case of repair, it's claimed when dealing with the diagnostic phase, so when you're actually trying to understand what happened, what to do about that. And I think it is important to distinguish between conservatism and robustness that I mentioned previously. In case of a subsea pipeline damage, where every case is unique, you may still try to classify the damage, as I mentioned before. Major damage, minor damage, and there's middle ground that is quite often the case. An example may be external impact that resulted in a concrete weight coating damage. Okay, you know that. You do not know what happened inside. So the pipe may be dented, may be bent. And here, during the diagnostic phase, it is important to be robust since you are dealing in the uncertainty field. And yes, in this regard, that's actually the case. Most safety factors exist because of experience has shown where uncertainties exist. In the context of this discussion, subsea repair systems operate in environments where intervention is expensive and difficult, and sometimes even impossible to override once installed. A repair that fails may require another major offshore campaign or even result in production shutdown. And so what sometimes appears conservative is often simply a method of managing the uncertainty.
Mm-hmm. I hope this next question isn't a silly one, but is there any point where engineering judgment sort of takes over from this standard or overrides this standard?
It's very important to distinguish between, again, judgment and critical thinking and the tool. At the end of the day, a standard guides the process, but the interpretation of the results remains an engineering responsibility. And I think that in many ways, standards create the foundation upon which sound engineering judgment can be exercised. A standard provides the framework, but at the end of the day, the qualification has to be judged by an engineer. Moreover, when we are talking about standards, it's important to know that at the end of the day, RP-F113 is 20 years old. So it had to stay up to date. And you only can do that when you have the engineering judgment. So it's like one of the cases is like we have been witnessing the technology evolution. I don't know, last year I presented a paper where we actually talk about the evolution. 1960s was hyperbaric diving. Nowadays we have remotely operating or unmanned vehicles employing some machine learning algorithms within them, or even real-time inspection methods. And this has to be also replicated within the standards. And in my opinion, this can only be done when you do have the engineering judgment behind that. You can actually understand what you may have and what you can do with that.
How important are qualification, documentation, and quality assurance when it comes to getting those repairs right?
One may see that as bureaucracy, I believe, but to me, they are absolutely fundamental at the end of the day. Because like in this context, a repair system has been designed, tested, and qualified, but it may remain unused for years before deployed. And actually, hopefully, it will never be deployed, but it may remain unused for many years. And when needed, it must work exactly as intended. This is why the RP-F113 places such a strong emphasis on qualification programs, manufacturing verification and traceability, testing, documentation, and quality control. If something has not been properly documented, demonstrated, and verified, confidence in its performance is reduced. And RP-F113 covers repair systems that are going to be needed in the case of an accident. You do not want your emergency parachute not to work if the time comes, And quality assurance here actually transforms the design into a dependable repair solution.
Lovely. Now, we like to look ahead on this podcast. So if we're looking ahead at hydrogen or CO2 service, how well do existing frameworks like RP-F113 translate to these newer use cases?
I actually like this one because just this year I was working on the repurposing for hydrogen pipelines. And so I had to go through the framework. So I think the underlying framework, not just the RP-F113, but the whole framework that I mentioned previously, actually translates very well, especially given that they do not operate in a vacuum, but are part of greater systems of standards and codes that are more or less harmonized. And so the processes of risk assessment, qualification, repair planning, and integrity management as well remain largely the same. The challenge lies in the material-specific interactions with the transported fluid. So like for hydrogen, for example, concerns include hydrogen embrittlement and crack growth rate, and also material compatibility due to differences in microstructure, low versus high-grade heat-affected zones. While for CO2 systems, impurities management and fracture propagation in dense space conditions are critical. And I think that even there, this framework works well because it actually is based on risk assessment and probabilities. But even in addition to that, the industry itself is already addressing these issues. For example, through new guidance, this year, DNV has published the RP-12 specifically for hydrogen pipelines. Plus, there are currently the joint industry projects called CO2 Safe Pipe and H2 Pipe JIPs. And obviously, these are being based on the existing framework. So first means that the existing framework allows that. And second, even if there is something, it means that it allows actually staying up to date on all the fronts, So I think that it does translate very well there.
Great. It builds the framework on which those new standards come out of. And I wonder how the digital world influences how standards are developed or applied. Maybe it doesn't.
Well, they do, because as I mentioned before, the technology itself has been developing quite fast, and especially in the later decades, I believe. And one big part of that is data itself. So one example, in my opinion, is the risk-related assessment that rely on probability data. You want, at the end of the day, to have a more conscious diagnosis when you talk about subsea pipeline repair. And thus, typically, the more data you have, the lower the level of uncertainty is. And modern inspection technologies generate vastly larger data set than before, and more will even allow real-time monitoring due to, high-resolution surveys, laser scanning, optic fiber, and digital. And data is both better and more available, and it's also digitalized. But even there, you need actually to go through that because most of the standards still are being worked on right now, do add this criteria that the level of certainty that you have in your data has to be high. And thus, all this digital data at the end of the day needs to be analyzed quite well. And so for engineers performing the fitness purpose assessment, improved inspection data and its faster assessment, reduce uncertainty and support more reliable conclusions. And if it is done in a timely manner, it's actually due to the fact that most of the data being digitalized. And all this is, and I believe will be further incorporated in the industry standards.
Great. Now, the August issue of World Pipelines includes an article from DNV on evolving subsea repair methods. So readers can look out for that. To finish us up today, Rustem, are there mistakes or issues in pipeline repair that you feel that we should have solved by now, but they still come up?
Certainly. there is always a place where you can improve further. One example, I think, it's that engineers can perform some sophisticated calculations. But at the end of the day, the conclusions are only as reliable as the inspection information that they are based on. And the more information, the better. And even more so, the more structured it is, the more the more flow it has, the better you may see the marginal differences there. And the problem that I see nowadays still is the tendency to treat pipeline integrity as a periodic activity rather than a continuous process. And I believe that successful integrity management depends on good baseline data, consistent monitoring, timely assessment, and repair preparedness before an event occurs. And all that actually requires operators and everybody to treat the repair parts of the last quarter of the life cycle, at least in the DNV's framework, as something continuous that has to be worked on repeatedly. And I'm not sure if it is, 100% like that throughout the industry. But that's actually the ultimate central message of the RP, in my opinion, that repairs do not start when damage is discovered or found. They start years earlier through preparedness, technology qualification, and obviously the engineering judgment, the engineering foresight. In a way.
Thank you so much for talking to the podcast, Rustem.
Well, thank you for having me. I would also like to thank my senior colleague, Roberto Bruschi, who gave me the opportunity as well.
That was Rustem Khalikhan at DNV, offering his expertise on enduring pipeline subsea repair standards and how they continue to serve the industry today. Don't miss the August 2026 issue of World Pipelines for that article from DNV on evolving subsea repair methods. Thanks for listening to the World Pipelines podcast. Subscribe for free and please rate and review. World Pipelines helps oil and gas pipeline professionals stay informed about the midstream oil and gas sector, offering technical articles, regional briefings, project and contract news, and think pieces on pipelines all over the world. Register to receive a print or digital copy at worldpipelines.com and search World Pipelines on LinkedIn to join our community.